Okay, I will continue. So we already learned the data reduction. The first is dimensionality reduction. The second is numericity reduction. And the third is data compression. The concept is like this one. We have raw data. We have column, we have row. And we want to compress. Compress means we want to make it smaller. And the smaller size is the smaller of the column and the smaller of the row. So when we compress, it means we want to make it small and small in these two dimensions. So there are some compression things we can learn. First is the string compression. String means text. So if you have text, so we can make the compression. There are extensive theories and well-tuned algorithms, and typically lossless. So we will check what is lossless. But only limited manipulation is possible without expansion. And then we can also do with the audio or video compression. It is typically lossy compression with progressive refinement. String, usually you can see it in the news. Maybe the newspaper will write a lot of content, but some of the newspaper, they can make summary. So you can use the compression. Or video compression. You like to watch football? Football match is 90 minutes, 45 minutes from one and 45 minutes in the second half. Maybe people do not want to look at the whole match, 90 minutes. They want to see only the highlight. So you can compress. Because this is the compression. And we can also do with the compression in time sequence. If we have data in the time, it is very long, so we can make it as a short time. So we can say this is also a kind of compression. So dimensionality and numericity reduction may also be considered as forms of the data compression. So if you do with the dimensionality reduction, if you have columns, you want to reduce it. And then if you have data in the rows and you want to reduce it. So you can combine between those methods. That's also a kind of data compression. So the types of the data compression, we can have lossless and lossless. Lossless means when you have the original data and then you compress the data. Once you want to return back to the original data, then you can get the original data. You can get the real original data. Because this is the loss. So there is no loss when you compress the data. But lossy means when you compress the original data, you cannot return back to the original. You can only approximate. So the original data is only approximated. The truth. So we cannot get the real loss. We can just say it is the approximation of the original data. So the lossless and the lossy. Okay, and yeah, this is the learning check, the first part. How many data reduction strategies do we learn? We have 3. Okay. So the first is dimensionality reduction. And the second is numericity or volume reduction. Numericity reduction. And the third is compression. Okay, so we learn 3 strategies: dimensionality reduction, numericity reduction, and data compression. So how many dimensionality reduction techniques do we learn? Yeah, we learn at least 4. The first is wavelet transformation. And then the second, we learn about PCA. Okay. And then we learn about the attribute selection. And then we learn about the attribute or feature creation. So we can combine some features and we can create a new feature. So that's about the dimensionality reduction. How many numericity reduction techniques do we learn? We have the parameter, okay, parameter methods, and we have non-parametric, okay, non-parametric methods, non-parametric methods. In the parametric methods, we learn about the regression analysis. So you can have the model. We assume we have the model, and then yeah, we can reduce the data based on this regression analysis. Maybe some of the data within the line, we can choose it. Or the non-parametric methods. The non-parametric methods, we use the histogram. Last time you learned about the pinning. We have the equal width. We have the equal frequency. Okay. We can use another methods like clustering, and we can use another method like sampling. Okay, so in the sampling, we learn the simple random sampling. We learn about the sampling with replacement. We learn about the sample without replacement. We learn about the cluster sample. We learn about the stratified sample. Okay. So yeah, there are many techniques that we learn. Can you mention any type of data compression? So we learn the examples about the string compression. We learn about the video. We know about the time sequence data. And there are 2 types of data compression, which is lossless and lossy. So the lossless data compression means you can get the original data, but the lossy means you cannot get the real original data. The original data only the approximation. Okay, so this is about the data reduction. Now let's move to the new section about data transformation. In the data transformation, it is a function that maps the entire data set in the entire set of values of a given attribute to a new set of replacement values. Subject to its old value can be identified with one of the new values. So some methods, you can use smoothing. Smoothing means we want to remove noise from the data. We can use attribute or feature construction. So last time you learned how to construct a new feature. So the new attributes constructed from the given ones. Aggregation. So I teach you how to use the orange to aggregate some columns with the sum function, or we can construct the data cube. And today we will learn about the normalization. We want to scale the numbers to fall within a smaller specified range. We will learn the min-max normalization, we will learn z-score normalization, and we will learn the normalization by the decimal scaling. And we will learn later about the discretization with the concept hierarchical climbing. Let's see the first about the normalization. We have min, max normalization. Min, it is the minimum. Okay. Max, mean the maximum. So if we want to normalize a numerical value, we need to check which one is the minimum and which one is the maximum, and we can determine it to the new minimum value and to the new maximum value. Okay. So this is the formula. The phi prime is the result. So the phi is the value that you need to minus with the minimum of the value in that attribute divided by the maximum of the value in that attribute minus by the minimum of that value in the attribute. Multiply by the new maximum minus the new minimum plus new minimum. Now, one example. I have the data about income. So the minimum value is 1000 and the maximum value is 8000. I want to normalize it to 0 until 1. Then the new value of this normalization, this will be 0. And the new value of 8000, it will be 1. Then how can we create the value? I would like to know if I have a value 6000. So 6000, it will be around here. So what is the value of 6000 in the range of 0 and 1? Okay. So we can use the formula. 6000, this is the value that I want to get, minus by 1000. 1000 is the minimum. Divided by 8000 minus 1000. 8000 is the maximum, 1000 is the minimum. And multiply by 1 minus 0. 1 is the new maximum and 0 is the new minimum plus the new minimum. So we get this value. Then I can say that, okay, if I have a value 6,000, then I can transform it into a value of 0.714. And this is based on the value 0 is 1,000, and then we have the maximum 1, which is 8,000. Z-score. What is Z-score? Because the Z-score normalization, if we know the mean and we know the standard deviation. So let's say I have the mu. Mu is the mean of the population, and then tau is the standard deviation. In the mean is 5,000 and the tau is 1,250. Then if I have a value of 6,000, I can just calculate it with this formula. P prime equals to the V, which is the value, minus by the mean of that attribute, divided by the standard deviation of that attribute. So the value will be 6,000 minus 5,000 divided by 1,250. So the value is 0.8. This is the normalization based on the Z-score. When we want to standardizing the numerical data, as I explained to you in the previous one, we used the Z-score, and the Z-score is based on the raw score that you want to standardize, and then you need to know the mean, and you need to know the top standard deviation. And the distance between the raw score and the population mean in the unit of standard deviation. And you can see that the negative score will happen if the score or the raw score is below the mean, and it will be positive when it is above. For example, you know that this is 6,000, right? 6,000 minus 5,000, of course, is still positive. But what about if I want to normalize 4,000? Then it will be 4,000 minus 5,000 divided by 1,250. Because 4,000 minus 5,000 is minus, then the normalized value will be also minus. Okay. There is an alternative. We can calculate the mean absolute deviation. Mean absolute deviation. It means that we do not use this standard deviation. Instead, we will use the deviation. The deviation means we want to check the raw score minus by the MF. What is the MF? MF is the average x1 plus x2 plus xn divided by n. It is the average. And we want to find the deviation of the raw score with the average. The raw score with the average. The raw score with the average. And we will do the absolute. So the standardized measure with this Z-score have the formula like this one. In the above formula, we use the mu and the standard deviation. But here we use the mean and we use the deviation or the absolute deviation. So some statisticians, they mentioned that using mean absolute deviation is more robust than using the standard deviation. So let's see the examples. The common standard deviation is using the mean square error. So this is using the standard deviation. We will calculate it with the mean square error. We have the mean absolute deviation. Now, I have this data. 90, 75, 85, 100, and 80. So the total will be 430, and then the mean is 86. So if I want to see the error for every of the values, I will just subtract 90, which is the original data, minus by 86, which is the average. And then I will do the square. So for square, it is 60. And then the second data, I have 75 minus 86 and then square. The result is 120. I have all this data. I can do the summation and I will divide with the number of data, 5, and I will do the square root, SQRT. SQRT means square root. So the result will be 8.6. I have the same data, but now I'm going to use the mean absolute deviation. With the mean absolute deviation, I will do the same at the first time to get the average. But now, in order to calculate the deviation or in order to calculate the error, I will use only minus 90 minus 86, and then if it is negative, I will put it as positive because of this absolute. So we have 4, 11, 1, 14, 6, okay. So we have the M80, we call it M80, 39 divided by 5. So this is the result. Why people say this is more robust? Because this usually, not always, usually is less than this standard deviation. So people say that this error rate is have a low range or smaller range than the square. And then if you have this one, you can make the z-score normalization. So the z-score normalization, this is based on the z-score with the standard deviation. We got 8.6. So what is the value? 90 minus by the average, which is 86, divided by the standard deviation, which is 8.6. So we get this value. What about using the M80? We have the value 90, the same. We minus with the average 86, divided by the M80 result, which is 7.8. So the only difference is only the division number. This is divided by 7.2. This is divided by the 8 points. That's the difference between the M80 and the MSC. Okay. Now we need to understand also the normalization by the decimal hill. In this formula, we have V divided by 10 power of j, where j is the smallest integer such that the maximum of the phi prime is less than 1. Okay, so it might be confusing. So let's see by example. So we have that formula. Let's have the input data. Minus 10, 201, 301, minus 401, 501, 601, and 701. I want to normalize the data with the normalization by decimal scaling. So the step one is I need to select the maximum value. Why? We need to select the maximum value. Based on the condition, we need to find the maximum of the absolute of P prime. So the maximum value now we can get the 701. So this is the maximum. Okay, be careful. We have the absolute here. Iterate j until it satisfies the condition. So j is the smallest integer. So let's say j starts with 0. Oh, sorry. J starts with 1. J starts with 1. If j is 1, what happened? So we have 701 divided by 10 power of 1. 701 divided by 10. It is 70.1. 70.1. Is it less than 1? No. Then we go to the next j. So let j equals to 2. 701 divided by 10 power of 2 because j equals to 2. So it means 701 divided by 100. So the result is 7.01. 7.01. Is it less than 1? No. The condition should be less than 1. So it is still not less than 1. Then I go to next, j equals to 3. When j equals to 3, then 701 divided by 1000. We can get 0.701. Is it less than 1? Yes. Then we will use the j equals to 3. It satisfies the condition. And we will divide all the numbers by 1000. So the normalized data will be minus 10 divided 1000. 201 divided 1000. So this will be the new data after the transformation. Okay. So you can see for every of this data. This is the result after we normalize it by dividing with 1000. Okay, let's see with the orange. Okay, let me just use the iris. And then you can see the pre-process. Okay, so when we are in the pre-process, you will see that the orange, the tool, they give you some only they give you only 5 options. Okay? When you want to normalize, you can normalize based on the mu equals to 0 and standard the variance equals to 1, or you can choose the center equals to 0, or you can choose whether you want to scale it to the variance equal to 1, or you want to normalize and the interval is in between 1 and -1, or you want to normalize from 0 until 1. So let's say if I want to normalize between 0 until 1. So you can get the values for every of these attributes. Now it has been changed. The original value is like 5 or 3 or 6, but now it becomes in between 0 until 1. And you can check this one. After you do this normalization, maybe you can check on the distribution. Okay, you can check on the distribution, the sepal line, for example. So now it becomes in between 0 until 1. Okay. So it has been transformed. And let's say if you want to check the scatter plot. So we have petal length and we have petal width. And now the value is also in between 0 till 1. 0 until 1. This is for the petal length for the petal width. And if you look at this chart, the representation is still the same with the original here. Because I think all of the units are the same. So if the units are different, then the top will be different. So next is about the discretization. In the discretization, you know that we learned the data types. There are 2 types of data type. Categorical data and then numerical data. We call discretization because we want to make it as a discrete problem. Discrete. What does it mean, discrete? Discrete actually, it represents the categorical data. And when we want to discretize, we need to consider the 3 types of attributes. The first is nominal data. You know that the nominal is an unordered set. Color, profession, it is no order. But we can also have ordinal data. The ordinal data is from the order set. And we have the military or the academic rank. Okay. So we have the sequence. Maybe the first is the student, and then they can promote it into teacher. So there will be an order. But we can also use the discretization from the number. The real numbers, let's say it is integer or real numbers. So the discretization, it means we want to divide the range of a continuous attribute into intervals. Okay, the keyword is one. Continuous attribute or numerical data into some intervals. Let's say I have the age 25, okay, 25, 30, 32, 35, and then 46, 51, 61, 65. Okay. So maybe I can say that the age below 50 is young, and the age after 60 is senior. Okay, then it means we want to make intervals. Okay, I guess I need to stop here.